Hey guys, Jake here, coming at you with another math lesson today. Today we're going to be going over another problem from my book, The Elite Guide to AP Calculus AB. It's available on Amazon. Actually today, the day this video is coming out, is going to be the last day that you can get the ebook version for free on Amazon. And I'll probably be raising the price of the paperback here pretty soon. So if you're interested in getting a copy, go check that out. You can scan the QR code in the upper right hand corner of your screen or go search The Elite Guide to AP Calculus AB on Amazon. You'll find it. But in my last video, I went through a problem talking about one-sided limits, and I want to kind of continue that discussion with another example. In the last example, we had a problem where we used this kind of method that I talk about in my book to find one-sided limits, but it wasn't necessarily super necessary to use that method. This example is a little bit more interesting because I think using that method actually gives us a little bit easier of a problem to solve. So I wanted to show an example where that was the case. And this is a little bit harder of a limit to find. And I think that should be probably a little bit more obvious just kind of looking at the problem here. So the problem we're going to do is, does the limit as x goes to 0 of f of x exist for this function f of x equals, and it's a piecewise function, where when x does not equal 0, we use this function x minus the absolute value of x all over x, and then when x does equal 0, f of x is just 2. So we can see here, obviously, we're looking at the limit as x approaches 0, so we're going to be looking at this piecewise function. It does seem like what we have here is some sort of a perhaps continuous function that's continuous everywhere except at 0. And then we have this kind of jump discontinuity, which is a topic that we'll get into in some future videos. But essentially what we probably have is a function where you have a continuous straight function, except there's a hole somewhere, and at that hole you have another point above or below it, probably something like that. However, that doesn't really matter too much. What's happening at x equals 0 does not matter for this problem because, again, limits don't care what's happening at that x value. The limit as x goes to 0 does not matter at all what x is at, or what the function is at x equals 0. What the limit cares about as x approaches 0 is what's happening around x equals 0. So essentially, we're going to be looking at just this part of our piecewise function. This part down here doesn't really impact anything. And we're going to be looking at both the left side and right side limits. So to do that, in order to prove if this limit as x goes to 0 of our function exists, we need to find both one-sided limits, and both one-sided limits would need to equal each other. We need the left-hand limit, the left-hand one-sided limit to equal the right-hand side limit. Those need to both exist and they need to be equal in order for this limit to exist. So that's kind of the general goal of what we're trying to show here. So basically, we're going to have the limit as x goes to 0 from the left of our function, x minus absolute value of x all over x. And then we're going to have the right-hand limit. So we're going to have the limit as x goes to 0 from the right of x minus absolute value of x all over x. So we need to find both this left-hand limit and right-hand limit. So the idea or the concept that I showed in my last video was to kind of convert this into something that's slightly different limit that maybe gives us something a little bit easier to solve. Or at least something a little bit easier to kind of conceptualize and wrap your head around. So what that concept is telling us is for the left-hand limit, for x as x approaches 0 from the left, we want to change x into 0 minus h. So 0, because 0 is what our x is approaching. So this number right here will just be whatever this number is here. For the left-hand limit, we're always going to do minus h, and for the right-hand limit, we're going to do plus h. And the reason we do that is because then we can rewrite this limit as x goes to h from the right side. So h is going to be a very small positive number, and that's going to be the case for both of these limits. Limit as x goes to h from the positive side, the right side. And then we're just going to basically change this function by substituting 0 minus h in for x. Well, 0 minus h is just negative h, and then 0 plus h is just h. So in our left-hand limit here, we're going to get minus h minus the absolute value of negative h over negative h. And then for the right-hand limit, we're going to get 0 plus h is just h. So we're basically just going to get the same function here, but with h instead of x. Okay, so the reason why we like to do this, or the reason why this can be kind of helpful, is these limits are maybe a little bit easier to kind of wrap your head around, because we know in both cases h is a small positive number. So as x approaches h from the right, I'm sorry, I messed up this here. This should not say as x approaches h from the right. Sorry. This should say the limit as h approaches 0 from the right, and as h approaches 0 from the right. So this is always going to be the limit as h approaches 0 from the right. This is not only 0 because we had x approaching 0. This is always going to say h approaches 0, no matter what your x was approaching. What the x was approaching affects this part of it right here, but not this part of it right here. So just to clear that up, sorry about that, miswrote that there. But the reason why this is nice is we know that h is a very small positive number. It's a number that is getting closer and closer to 0. So it's very, very small, and it's getting smaller as our limit is kind of approaching the value we're looking at. But it's a small positive number. So the reason why that's kind of nice, and I'm sorry, I made another typo over here. The reason why that's kind of nice is it's a little bit easier in a lot of cases to kind of wrap your head around what's happening with a function when you know that you're dealing with small positive numbers instead of having to kind of keep track of, negative parts and positive parts to some extent. So the other thing that's kind of cool in this case is we have h is a very small positive number. We also have these absolute values that kind of make things a little bit weird. So what's interesting is since h is a very small positive number, what's in the absolute value here is negative h. So negative h is going to be a negative number. But then we have the absolute value making it positive again. So essentially, the absolute value of negative h is just h. And we know that h is positive because we're approaching 0 from the positive side. So this absolute value here will essentially, because the absolute value of negative h is positive, so is h, that will just be negative h is really not going to change. That's still negative h. Then we're going to have minus h, because again, h is equivalent to the absolute value of negative h, because it's positive, all over negative h. So negative h minus h all over negative h. This will essentially just simplify into the limit as h goes to 0 from the right of negative 2h over negative h. Oops. The negatives are going to cancel, the h's are going to cancel, and this is essentially just going to give us 2. Okay, then for the right-hand limit, again, we have something kind of similar. Because h is approaching 0 from the right, it is a very small positive number. That means h is positive. That means the absolute value of h is just h, right? Taking the absolute value of a positive number doesn't change its value. So this is just going to be the limit as h goes to 0 from the right of h minus h over h. Okay, so h minus h on our numerator is just 0. So we have the limit as h goes to 0 from the right of 0 over h. And now this is where it's kind of weird. We don't really want to think about this as just plugging in 0 for h, because if we think about it that way, we're basically getting 0 over 0, which is undefined. That doesn't really work. However, what we essentially have here is a fraction where the numerator is 0, the denominator is some very, very small positive number. It's true that h is approaching 0. It's never actually going to reach 0, though. H will not ever be 0. H will be a very small positive number. It doesn't really matter what that small positive number is. What matters is that it's not 0, because we can't divide by 0. So essentially what this limit is giving us is 0 over some positive number, right? Which 0 divided by any number is just 0. So our right-handed limit gives us 0. Our left-handed limit gives us 2. So our left-hand limit and right-hand limit are not equal to each other. Therefore, this two-sided limit does not exist. So I hope you got some value out of this video. If you did, do me a favor, hit that thumbs up, and go check out the Elite Guide to AP Calculus AB, available on Amazon. We'll keep working through some more problems from the book in the coming days, weeks, months. So I'll see you for the next one. Thanks.